हेलो स्टूडेंट्स, वेलकम बैक टू माय यूट्यूब चैनल फिजिक्स क्लब बाय शक्ति सर। आज के लेक्चर में हम एक्सेलरेटेड प्योर रोलिंग पार्ट बी को डिस्कस करेंगे। इस सेक्शन में मैं आपके सामने 4 एग्जांपल्स लेके आऊँगा एक्सेलरेटेड प्योर रोलिंग के ऊपर। बिल्कुल ही अकॉर्डिंग टू द कॉन्सेप्ट एग्जांपल्स हैं। इन 4 एग्जांपल्स को समझ के आपको एक्सेलरेटेड प्योर रोलिंग हॉरिजॉन्टल डायरेक्शन में तो बिल्कुल परफेक्ट हो जाएगा। चलिए वन बाय वन डिस्कस करते हैं इन एग्जांपल्स को और अपने कॉन्सेप्ट को रेडी करते हैं। अब देखिए, एक्सेलरेटेड प्योर रोलिंग जो है मेरे पास, उसमें कहता है कि ए टेंजेंशियल फोर्स F इज एक्टिंग एट द टॉप ऑफ द थिन स्फेरिकल शेल। सो ये जो फोर्स एक्ट कर रहा है यहाँ पर एट द टॉप ऑफ द थिन स्फेरिकल शेल। अब स्फेरिकल शेल है, इट मीन्स इट इज़ ए हॉलो स्फीयर of mass m and radius r. Find the acceleration of the shell if it rolls without slipping. So there is no slipping. Actually, it clearly mentioned that it is under the pure rolling, but force is acting on the hollow sphere. It means that it is accelerated pure rolling. So for the accelerated pure rolling to takes place, at this point there may be a high chance that the friction will act at this point. So we will determine the direction of the friction, and maybe if required we can calculate the magnitude of the friction also. So let's get started. So first of all we will consider, let's say, the direction of the friction acting on this hollow sphere is F. This is the direction of the friction, let's say, right? And according to our previous concepts, we have also discussed that the first fundamental equation in this type of situations is the translational equation, that is the net force acting on the system must be equals to the mass into acceleration. So this is our first equation. And from the rotational perspective, the second equation is that belongs to torque, that is the torque applied by this force is in this direction, that is clockwise direction, but the torque applied by the friction about the center of mass is anti-clockwise direction. So the torque by force is positive and torque by friction is negative. So our second equation for rotational motion can be written as Fr, that is the torque due to force minus torque due to friction, is equal to I alpha. And alpha can be replaced by A upon R, correct? Because we know that A is equal to R alpha. So we can simplify this more. Force minus friction can be written as I A upon R square. This can be the situation. Now let's say this is our equation number second. We can add equation first and second. By adding just equation first and second, this positive value of friction and the negative value of friction will be cancelled out. So our net can be written as 2F is equals to mass into acceleration plus I A divided by R square. But furthermore, we can plug the value of moment of inertia of the hollow sphere or shell, which is equals to 2 by 3 mr square. So I am writing ma plus mr square and 2 by 3 a upon r square. So there are few values which can be cancelled, r square cancelled with each other. So we are now dealing with ma plus 2 by 3 ma, which comes out to be 5 by 3 ma from this situation. So it is equals to 5 by 3 ma. So actually now we have 2F equals to this value. So F can be written as 5 by 6 ma. This is the value of F in terms of acceleration. So the acceleration can be written as now 6F by 5m is nothing but the required acceleration in this question. Okay, so this is our answer for this question. So it is quite straightforward. just applied the translational equation and the rotational equation, plug the value of moment of inertia, and you will good to go. Let's move to our example number second. So this is our example number second. Again, quite straightforward if you understand the first example. What it says, a horizontal force F acts on the sphere at its center as shown. So this is the point of center of mass, and a horizontal force is acting on this sphere. Coefficient of friction between the ground and the sphere is mu, which helps us. So here we have the value of mu. So this will help us to calculate the friction. And rest, it is saying what is the maximum value of force F for which there is no slipping. So again, we need to find the maximum value of force F so that there is no slipping. Make sure we don't know the value of friction, so our answer must be in terms of mu or mass m. Okay, so again, so what is our strategy? The point number one, step one is applied the translational equation. So let us consider again the force of friction acting in this situation is in the forward direction. We can assume that, let's say, it is acting in the forward direction. Okay, if it comes out to be negative, then we can turn it around. But still, logically even we can think about something, as at this situation this point of contact is accelerating in the forward direction, and also due to this force it has a tendency to rotate in the clockwise direction because of the friction, right? So let's start the situation. The translational F minus F can be written as mass into acceleration. This is our equation number first, correct? This is our translational situation. And the rotational part, so here we need to consider that the external force is passing through the center of mass. It implies that no torque is acting due to this external force, because it already passing through the center of mass, and we are calculating the torque about the center of mass. But due to this frictional force, which is not passing through the center of mass, will apply a torque on this sphere in this sense. All right, so let's write the situation. So torque is equal to I alpha, and I, so alpha can be written as A upon R. Further, we can write torque is nothing but the force of friction times radius, and for sphere the moment of inertia is 2 by 5 mr square A upon R. So friction can be written as 2 by 5 mr square times A upon R square. So R square terms will be cancelled out. So our friction value can be written as friction is equal to 2 by 5 ma. This is our friction value. We can write this equation as our equation number second. Now, as we did in the example number first, we can simply add equation first and second, right? So let's, or here we need to we no need to find the value of acceleration, so we can make our equations independent of acceleration. So here from this situation you can see the ma term can be written as 5f divided by 2 is equals to mass into acceleration. We can plug this value of acceleration. We can plug the value of acceleration here. Okay. So let's plug the value of mass into acceleration. So it is F minus friction is equals to 5F divided by 2. So external force acting on the body is equals to friction plus 5 by 2 friction, which comes out to be 7 by 2 friction. So this is the external force which is acting on the body in terms of friction. But we are given mu, that is the coefficient of friction between the sphere and the ground. So we will write our equation in terms of mu. So guys, we know that friction is what? Friction is less than or equals to mu mg, right? And from this situation, we can write friction as 2F by 7 is equal to friction. So we can plug the value of friction here, that is 2F by 7 must be less than equals to mu mg. So from this situation, the external force F is equals to 7 by 2 mu mg. So this is the required value of external force applied on the sphere under which there is pure rolling. Okay. So what is the maximum value? The question is asking what is the maximum value of force for which there is no slipping, right? So this is the maximum value. And how we did know? Because we use A is equal to R alpha. We use this equation, and if this equation is satisfied, it means that we are obeying the pure rolling conditions, right? All right. Let's discuss the next question, example number 3. So example number 3 is saying if force F is applied at the top of the disc of mass 4 kg and radius 0.25 meter, find the maximum value of force for no slipping. Actually this is the similar question but with some values. So let's solve this question. So mu is given, so it's clearly hint that the friction, we can write the friction somewhere here, the friction is acting. So let's write our first equation, that is the external force plus friction is equals to mass times acceleration, and our second belongs to torque, that is force R minus friction R is equals to I alpha, and alpha can be replaced by A upon R. So we can take these R out, and let's F minus friction can be written as I A divided by R square, where I is the moment of inertia of this, it is a disc, right? So it is 1 by 2 mr square, 1 by 2 mr square times A upon R square. So R square terms going to be cancelled out. So it is m A divided by 2. So here we have our first equation, here we have our second equation. Now we have our two equations. Again we need to find the maximum value of friction in terms of mu. So let's make our equations independent of acceleration, because we don't need any acceleration, we are not going to calculate the acceleration. So from equation second, we can write 2F minus 2 friction is equals to mass into acceleration, and let's plug this value in equation first. So equation first going to be written as F plus friction can be written as 2F minus 2 friction. So F minus, we can make it like this. So 3 friction is equals to 2F minus F So 3 friction is going to be external force F. So again the frictional force is like this, but the maximum value of friction can be written as mu mg. So here the value of mu, so we can plug the situations here. So that is, in place of friction we can write F by 3 less than equals to mu mg. So F less than equals to 3 times of mu mg. So F less than equals to 3 times mu is equal to 0.6 and mass is equal to, I think, given 4 kg, and let's write the value of G 10. Okay. So friction comes out to be 6 4 is 24, 3 times 24, 3 times 24. So we can easily calculate this situation, 3 times 24, which is 72. So force can be less than or equals to 72 Newton. So this is the answer of this question. If this force will applied on the disc, then so this is the maximum force we can apply on the disc here at the top, here at the top under no slipping. Okay. So let's move to our example number 4. So example number 4 is a little lengthy, but it's worth understanding this concept to strengthen our concept. This is a very good example. So it says a solid sphere of mass 5 kg and radius 1 meter is kept over a rough surface. That's why the coefficient of frictions are given, because it is a rough surface. A force 30 Newton is acting, which is given in the diagram, at the topmost point. Check whether the pure rolling will take place or not. So we have to find out about the pure rolling. So students, by solving many questions and understanding the concept, it is quite clear now, whenever the forces are acting at the top, like here, so make sure, or somewhere in between these situations, the friction will act in the forward direction. So here too the friction will act in the forward direction. Otherwise we can assume the friction will act in the forward direction, and if we calculate the value of friction and it comes out to be negative, it means that the friction is acting in the opposite direction. If the value of friction comes out to be positive, it means that the direction chosen by us in the diagram is correct. So let's say in this diagram, let's discuss this situation in this diagram. So we have now two coefficient of frictions, one belongs to static friction, one belongs to kinetic friction. So let's find out the maximum values available. The maximum values available for static and kinetic frictions. So we know N is equal to mg in this situation, right? So mg is acting downward direction, the normal reaction is acting in the upward direction, like this. So the value comes out to be, this is 5 kg and let's say g is equal to 10, so it is 50 Newton. 50 newtons. So from this situation we can write mu as N, which belongs to the static friction, is equals to mu is equal to 0.3 and this is 50, which is nothing but 15 Newton. This is the value of static friction, and mu Kn, again it is 0.2 times 50, it comes out to be 10 Newton. So this is the maximum value of kinetic friction. And it's very clear now what is the requirement for the friction for accelerated pure rolling. So what is the friction will do? Friction will help to satisfy the equation, that is A is equal to r alpha, right? So let's say in this situation it's a pure rolling, friction is sufficient. This is our assumption. Let's say the friction is sufficient to provide the pure rolling. It means this equation will be satisfied. So acceleration is what? Again I am using a little bit short form. So acceleration is net force divided by mass, correct? And alpha is what? Alpha is nothing but the net torque acting on the system and divided by moment of inertia. What is the net force in this situation? That is the external force plus the friction divided by mass and r. And if we consider the net torque acting on the system, that is external force times r minus friction times r divided by moment of inertia. And this is a solid sphere, so it is 2 by 5 mr square. Okay, these r terms going to be out from the bracket and then become r square. So r square and r square will cancel out. This mass term and this mass again cancel out. So we can write the situation. Let's write here F plus friction is equals to F minus friction, and we have 2 by 5, which means 5 by 2. 5 by, so m terms cancelled, m term cancelled, r square cancelled, correct? So now we have equation independent of acceleration. We will find the value of friction from this situation. So let's say by solving this, it is 2f plus 2 friction is equal to 5f minus 5 friction. So 7 friction is equals to 3 times of external force. So friction is nothing but 3 by 7 times external force. So this is the expression for friction. So friction can be further calculated as the external force is given 30 Newton, which comes out to be 90 by 7, and it is 12.85 Newton. So this is the requirement of friction for pure rolling to takes place, and this is the requirement, right? And let's see, this much friction is available, and if we look here, yes, this much friction available, because the static friction available is 15 Newton. So it is clearly mentioned availability is greater than requirement, so the situation will be fulfilled. It means the pure rolling will takes place in this situation. So one thing is very clear, the pure rolling will takes place. So first step, it's saying check whether the pure rolling will takes place or not, and by this calculation you can say that yes, the pure rollings will take place because friction is sufficient for accelerated pure rollings to takes place. Second step, it is saying find direction and magnitude of friction. So this is the magnitude of friction which is required, and yes, it comes out to be positive value. So it means the direction will be in this direction. The chosen direction is in this direction. That's why the torque applied by this friction is in the anti-clockwise direction and it is negative. That's why the torque here we write negative. And the net external forces we add these because we have considered the friction in the forward direction. That's why the net force acting on the system, we add these two forces. Okay, so the direction of the friction is in the right side, and the magnitude is 12 by 85 Newton. 12.85 Newton, that's the direction. Okay, second step is done. Find linear acceleration and angular acceleration. So now it's quite easy to calculate these two situations. The linear acceleration is nothing but A, which can be written as net force divided by mass. and the net force is external force plus friction divided by mass. External force is 3030 and friction is acting is 12.85 divided by mass, and I think the mass is also given, which is 5 kg, and you can easily calculate this situation, which comes out to be 8.57 meter per second square. So this is the acceleration of the sphere. Next thing they are asking in this situation is for alpha. So alpha is net torque and divided by, or let's make the smaller equation. So the smaller equation can be A is equal to R alpha. So alpha is equal to A upon R. We can use this smaller one. So it is 8.57 divided by R, and R is 1 meter. So it is again 8.57 radian per second square. So this is the value of angular acceleration of this solid sphere. So these are our answers for this problem, and it is a very important numericals to take place. Sometimes, guys, please listen, sometimes the coefficient of friction is different, or we can say we have the same situation, but the external force acting here is little bit higher. Then there may be a high chance that the pure rolling does not take place. For example, you can solve the same situation with 4040 Newton external force, and then see, do we have the necessary conditions, that is the requirement of friction for the pure rolling is still under 15 Newton or more than 15 Newton. If with 40 Newton external force acting here, the requirement of friction is more than 15, it clearly implies that the pure rolling does not take place and there is a forward slipping. Okay, so by this I am going to end this lecture. See you in the next, and if you are visiting my channel for the first time, please subscribe it, like it, and share with your friends. Wish you all the best. Bye bye.